Let us now try to understand how would the feasible set look like if we have got n risky assets. So this is a bit more complicated problem compared to the one that we studied last week, which had just one risky asset and one risk-free asset. And we'll soon see where the complication comes from. So first note that we'll still be working on the same mean standard deviation diagram that we did last week and that we have been looking at before. So we can start out by plotting each of these n assets whose mean and standard deviation we know as points on this diagram. The complication comes in from the fact that the different portfolios that we can make is much more complicated and manifold compared to the ones that we had before. So we can have portfolios which consist of each of these n assets alone, or it can be any combination of any number of these n assets, right? So we can have, let's say, if n is 10, we can have an asset which combines, let's say, 1, 2, and 7 only. Or we can have which combines 1, 3, 5, 7, 9, and so on, right? So you have like a lot of different combinations to think about. So what are the general set of portfolios that we can form? So these are the ones that are made by changing the weights allotted to different assets. And we should allow for all possible values of the weights such that the sum of the weights add up to 1, right? So as before, we can have some of the weights being negative that would correspond to the shorting case, right? So the set of points that correspond to the portfolios is what is called the feasible set or the feasible region. So in order to make things concrete, let us look at the special case when you have got n equal to 2, right? So what that means is that we have got two risky assets. So how would we go about understanding what is the feasible set here? So what we can do is introduce a variable alpha, which is going to define the weights W1 equal to 1 minus alpha and W2 equal to alpha. So this alpha is basically a number which tells us what's the weight of the second asset in the portfolio. And the remaining weight, which is 1 minus alpha, has to be the weight of the first asset in the portfolio. Now, why is this a good way to proceed? Because as we change alpha from 0 to 1, we are going to essentially end up covering a lot of different situations, right? So for instance, if we have got alpha equal to 0, that would correspond to the case where W1 is equal to 1 and W2 equal to 0. So the portfolio consists of only asset 1. Then as we increase alpha from 0 to 1, they're going to have a combination where we are going to have positive weight on both the assets. And finally, when we reach alpha equal to 1, then W1 becomes 0 and W2 becomes 1, so that the portfolio consists of only asset 2. Now, we can also have a value of alpha outside the range 0 and 1, and that would correspond to cases involving short selling. So what would be the rate of return of this portfolio as a function of alpha? So remember that R1 is the rate of return of asset 1 and R2 is the rate of return of asset 2. So therefore, R alpha is basically the rate of return of the entire portfolio. That's equal to 1 minus alpha R1 plus alpha R2, right? Remember, alpha is the weight on asset 2 in the portfolio. So we can easily calculate the mean value of this rate of return. So that is given by 1 minus alpha R1 bar plus alpha R2 bar. Again, R1 bar is the mean rate of return for asset 1 and R2 bar is the mean rate of return of asset 2. So we can see that the mean value is a linear function of the different rates of return as we expected. However, if we calculate the standard deviation, this is no longer necessarily a mean value, right? So the variance is going to be given by this expression that you see here, which is 1 minus alpha square sigma 1 square plus alpha square sigma 2 square plus 2 alpha into 1 minus alpha sigma 1 2. Sigma 1 2, remember, is the covariance of the rate of return between asset 1 and asset 2. And if you are taking the standard deviation, so that's equal to the square root of this expression. So keep in mind that this is the expression that you have. Do not make the mistake of just writing down sigma alpha is equal to 1 minus alpha sigma 1 plus alpha sigma 2. That would be an incorrect thing. Okay. So this looks a bit more complicated expression. But in order to make progress, what we can do is we can actually rewrite this expression in terms of the correlation coefficient. Remember that the correlation coefficient is the covariance divided by the product of the standard deviations. So this sigma 1, 2 that you have here, we can rewrite it in terms of the correlation coefficient in this way. Okay. And we know that the correlation coefficient is something which lies between -1 and 1. And so we can think about what is the bound of this value of the standard deviation, right? Why is this bound? Because notice that these are not dependent on rho. So the only place where rho comes in is in this expression. And therefore, we can actually think about what is the bound of this, right? So when you have got rho equal to 1, the upper bound for this expression that you see here is actually given by, if you put in rho equal to 1 here, you end up getting 1 minus alpha square sigma 1 square plus alpha square sigma 2 square plus 2 alpha 1 minus alpha sigma 1 sigma 2. Now, if you notice this expression, this is nothing but the square of 1 minus alpha sigma 1 plus alpha sigma 2. And so therefore, if you take the square root, you end up getting this expression, right? So notice that in the case where you have got rho equal to 1, the standard deviation is a linear function of alpha, and the mean is also a linear function of alpha, right? So you can actually eliminate alpha from both of this. And basically, you can also show that as alpha varies between 0 and 1, the portfolio is going to actually trace out a straight line between the 2 points. So we'll see a picture of how that looks like in practice later on. What about the lower bound? So we can use here rho equal to -1. And if we put that in here, then we end up getting an expression which is 1 minus alpha sigma 1 minus alpha sigma 2 whole square, and we are taking the square root of that. So this is given by the following absolute value, right? Now, when alpha is small, then this term is actually positive when you've got this 1 minus alpha sigma 1 minus alpha sigma 2. And as alpha's value increases, so once it crosses sigma 1 by sigma 1 plus sigma 2, this term becomes negative. And so therefore, this sigma ends up looking like this, right? So these are, in order to make things easier, think about this as like alpha is between 0 and 1. You are looking at the different extremes, and at some point, this sign is going to flip. And so you end up looking like this, okay? All right. So we can actually also look at some of these things implemented. So here we have got, again, two assets. The expected return of asset 1 is 5%. The expected return of asset 2 is 10%. Standard deviation of asset 1 is 20%. Standard deviation of asset 2 is 30%. And correlation is 100%, right? So therefore, this corresponds to the case where rho equal to 1. So the first thing to do is actually to plot the two assets. So the first asset is going to have a point which is 5%. Remember, expected return is on the y-axis and standard deviation is on the x-axis. So you have got 5%, and the standard deviation is 20%. So that's why this point is here. This orange point corresponds to one asset, asset 1. And the second orange point corresponds to the second asset, so expected return of 10% and a standard deviation of 30%. And as we discussed here, we are basically going to, by changing alpha between 0 and 1, we'll consider the short sales case later on. But for now, we are not allowing short sales. As alpha changes between 0 and 1, what's going to happen is that you are going to have the different points which lie on the straight line joining this, okay? But notice this corresponds to only the case when you have got rho equal to 100%. We'll see that as the value of rho changes, you end up getting different situations. So let's look at the other extreme case where rho equal to -1. So we have kept the same values of expected return and standard deviation of the asset. The only thing that we have changed is that we have changed rho equal to 1 to rho equal to -1. And in this case, this is the diagram that will kind of emerge. And you can see that basically there is a way of combining these two assets to, in fact, end up getting a standard deviation of 0%, right? We actually also discussed, if you read carefully, hint about what is the combination that will give us that, right? I encourage you to kind of like go ahead and derive it. Okay, but these were the two extreme cases. What happens if you have got rho between 0 and 1 or rho between -1 and 0? So this would be the same picture with the same expected returns and standard deviations, but now rho is 50% or 0.5, right? So in this case, this would be how the curve will look like. This is the feasible set in the expected return standard deviation space. And again, if you instead you have rho equal to -50%, this is again how the curve will look like now, right? So you can see that depending on the value of correlation coefficient, there are these different points which we can achieve by changing the weights on the different assets in the portfolio, right? Now, so far in our discussion, we have been assuming that you are not allowed to short the assets. So therefore, we are assuming that the weights are non-negative. What happens if you allow for the weights to be negative as well? So therefore, you allow the assets to be shorted. But remember, we still need to respect that the sum of the weights need to add up to 1. So this is how the diagram would look like, right? So this and this is the same diagram. All these numbers are the same, the correlation of asset, standard deviation, and expected return. The only difference is that in this diagram, we are considering the case where shorting is not allowed. And here we are allowing for shorting to be allowed, right? So you can see that one difference is that earlier you could not go along this curve beyond this orange line or beyond this orange point. And now actually this line extends much beyond, right? So that is typically how, if you allow for shorting, you have this kind of like phenomenon. Okay. All right. So these were about 2 assets. How would things look like if you instead you have got 3 assets? So this is a much more complicated picture, but the underlying inputs are still the same. So for each of these assets, you have got expected return. So for the first one, it's around, I think around 8%. And for the second one, it's around 12%. And for the third one, it's around 15%. The standard deviations are 15%, 25%, 25%. And now you have to actually state the correlation of asset 1 and 2, asset 1 and 3, and asset 2 and 3, right? Okay. So what you have here is first, these 3 circles represent the 3 different assets, right? So for example, this one represents asset 1, which has expected return of 8% and standard deviation of 15%. This one represents asset 2, which has an expected return of 12% and standard deviation of 25%. And this one represents asset 3, which has expected value of expected return of 15% and a standard deviation of 25%. So what these orange curves do is it tells us about what are the set of um, points on this expected return standard deviation plane that are possible to achieve if you are just using 2 of the assets, right? So for example, this orange curve is about what is possible if you are just using asset 1 and asset 3. This orange curve is about what happens if you are just using asset 1 and asset 2. And finally, this one is about if you are using just asset 2 and 3, right? However, these are not the only things that are possible, right? So you can actually use a combination of all the 3 assets. And these blue dots represent all the points that are actually possible if you are using the different 3 assets together, right? So you can kind of like go ahead and construct the feasible set with any general number of assets. But as you can see, the picture looks much more complicated compared to the 2 asset case, right? Okay, so there are some more terms you need to be familiar with. Let us go through them now. So suppose that you fix a particular value of the mean rate of return, then the feasible point with the smallest standard deviation is the corresponding left boundary point. Okay. And this left boundary of a feasible set is called the minimum variance set. And the point on the minimum variance set with the minimum variance is called the global minimum variance portfolio or the minimum variance point. So let's take a look here. So again, we have got these 3 assets, right? These are actually the same numbers that we had here. That we had done in the previous graph. And so let's look at what we are saying. So we are fixing a particular value of the mean rate of return. So suppose you want to fix the particular value at, let's say, 14%, right? Then what we are saying is that we want to look at the feasible point with the smallest standard deviation, right? So you have this 14%. You look at the feasible point with the smallest standard deviation, right? And you basically kind of like plot it here, okay? And you can do this for all the different values of expected return, right? So for example, for 10%, this would be a point which is here, right? And instead of plotting all these points, you just plot the one which is the leftmost point of this feasible set corresponding to the particular expected return that you are interested in, right? And if we do that for all the values of expected return, we end up tracing this green curve, right? Which we are going to call basically this minimum variance set. Okay. So this corresponds to the minimum variance that is possible for a particular value of the mean rate of return. Okay. Now, among all these points, the point on the minimum variance set with the minimum variance is called the global minimum variance. So if we go back to this figure, so this is the minimum variance set. Now, if we look at the point with the smallest variance, so this must be this point, right, which has the smallest standard deviation and therefore the smallest variance. So we are going to call this point the global minimum variance portfolio. Okay. And it's also sometimes called the minimum variance point. Okay. Now, why do we care about this line? So, or this curve? Let's think about it. So, imagine that you have an investor who has to choose a portfolio on a given horizontal line in the mean standard deviation plane. Okay. Now, what does that mean? So, horizontal line means that it's a straight line, right? So suppose you fix this line, right? The one corresponding to, let's say, 14%. Now you are asking that if we go back to this figure, you are saying that you have fixed this point 14%, and you have got all these different points which lie on this 14%, right? If you draw a straight line, there are many such points, right? The question is, among such points which lie on this 14% line, what is the one that the investor would actually end up selecting, right? And here, if we think about investors who have this mean variance preferences that we discussed last time, so they like mean but dislike variance. So if you ask these people, and these are, let's say, the risk-averse people in our world, then they're going to say that they want to select the portfolio corresponding to the leftmost point on the line, right? Why is that the case? Remember, we are thinking of people who dislike risk, right? And we have fixed the mean rate of return. So the only thing that is changing along these different points is the risk associated with them, where risk is measured through the variance or the standard deviation, right? So again, if we go back here, you have got all these points which have this 14% return, and you are asking somebody who likes mean but dislikes the standard deviation. Now the mean is fixed, so therefore the only thing that they can change is to reduce the standard deviation as much as possible, and so therefore they would want to end up with the leftmost point that is achievable here, right? So that's where we get this statement that they would prefer the one with the smallest standard deviation for the given mean. Okay. So therefore, now, if you think about it, this is exactly what we did about the minimum variance set, right? This is exactly the set of all points as that, fix a particular value of expected return. What's the lowest possible standard deviation associated with that in the feasible set? That's exactly what this minimum variance set is doing. So that's why we are interested in the minimum variance set. Okay. We could have asked a different question as well, which is that consider portfolios which correspond to various points in a vertical line, right? So this was about fixing the expected return before, and we were asking what's the smallest possible variance or standard deviation. Now we are fixing a vertical line. So suppose you fix it at 20%, and then you ask what's the smallest or the largest possible expected return actually, right? So these are, if you fix a vertical line and you are asking people to rank the portfolios along this line. So these are basically portfolios with a fixed standard deviation and various mean values. And most investors are basically going to prefer the highest point on this line, right? So they want to have the largest possible mean for a given value of standard deviation. And this basically refers to the property of non-satiation, right? So everything else remaining the same, investors always want more money, right? So what if you now combine these two insights, what we are saying is that only the upper part of the minimum variance set will be of interest to investors who are risk averse and satisfy non-satiation. Okay. And this upper part of the minimum variance set is what is known as the efficient frontier of the feasible region. And these are efficient in the sense that they provide the best mean variance combination. Okay. So if we now go back and think about it. So you have got these points. We have already argued that if you dislike risk, these are the only set of points that you want to consider. But now we are going even further and saying that suppose you have a choice between this and this, you would always prefer this, right? Because you have got both these points giving you the same standard deviation, but this one obviously dominates in the sense that it gives you a higher expected return, right? So therefore, the relevant point to consider from an investor's perspective who has this mean variance preferences is going to be this upper part of this curve, right? And this upper part is exactly what is known as the efficient frontier. So that's what we are saying. And what we want to do now is to actually get into more details about mathematically actually solving for this efficient frontier, the minimum variance set, and so on, right? So that's coming up next. And that is where we get into our discussion of the Markowitz model.